Hey guys, welcome back to another YouTube video. In today's video, I am going to be talking about a programming technique called recursion. Now, recursion is used to simplify a problem into a base case where it can then be solved. Now, this is extremely useful for solving a lot of problems like the one I'm going to be demonstrating here, which is the Fibonacci sequence. So calculating the nth Fibonacci sequence or number in that sequence based on just a given input. Okay, so let's get started right now. So before I actually talk about recursion, let's just understand Fibonacci because that's what I'm going to be doing an example on right now. So pretty much a Fibonacci sequence is the nth term is equal to the nth minus 1 term plus the nth minus 2 term. So to put it simply, 8 right here, which is the 6th term, would be equal to the 5th term, which would be 5, plus the 4th term, which would be 3. So 5 plus 3 equals 8. Same thing if we move up here to the 8th term. That is equal to the 7th term plus the 6th term, which equals, again, 21. Okay, fairly simple. So now, what is recursion, and how are we going to use it to solve this problem? So given the nth term, what is that value? Okay, so we're going to be using a function, and what recursion is pretty much calling a function inside of its own function. So if you name a function, if you call a function num, then that means you're calling num inside of num. And I'm going to show an example so that it'll be a lot more clear. So let's start off by defining a function. In this case, I'm going to call it fib. And now in the brackets, I'm going to give it one parameter called n, which is going to be the term number. Now we have to start off by using a base case. Now this is important for all recursion problems, is that you have a base case which is going to return a constant value. So our base case here is if n is less than or equal to 2, we need to return a value of 1, like so. Now, if it's not less than or equal to 2, well, what do we need to do? Exactly what I stated above and what the sequence states. So we need to return then the Fibonacci sequence of n minus 1 plus the Fibonacci sequence of n minus 2, like so. Now this looks extremely simple, and that's because it is. So if I try calling now the Fibonacci sequence of 8, what's going to happen is we're going to go up here, or actually let's use 4 because it's easier to explain. We're going to go up here, we're going to sub n for 4. We're going to say, is 4 less than or equal to 2? No, it's not. So now we're going to move here, and we're going to look for the Fibonacci of 3 plus the Fibonacci of 2. Now, the Fibonacci of 3, we're going to call this function again. We're going to move up here. The Fibonacci of 3, is that less than or equal to 2? No, it's not. So we move down here, and we say that's the Fibonacci of 2 plus the Fibonacci of 1. And then with that applies to our base case, so that'll be 1 here plus 1 here, which will be 2. And now that's just calculated the 3 part, so that's only done this first call on the 4. Now we move to the Fibonacci of what will be 2, because 4 minus 2 is 2. That applies to our base case, so that'll be 1. We have already calculated this value, which is 2. 2 plus 1 equals 3, and that is the value here for the 4th term. So I'll show you it working when I run the program like this. And I forgot to print it to the screen. Okay, so now I will print it to the screen like so. There we go. We get a value of 3. Now this is all great, but I want to show you a problem that happens. So we're going to run the Fibonacci of 10. You'll see it runs pretty quickly, and up to about 20, everything's running pretty smoothly. Now what happens if I try to put in a larger number, like maybe 35? Well, the program takes forever. So I know that one wasn't not extremely long, but think about that timing. So that took about maybe 5 seconds to get us that number. What if I go to 38? Well, now we are continually loading as the time to calculate has got exponentially longer. And this is the problem with recursion on a basic level. So you can see we just got our answer now, which is kind of unacceptable for this program. So how can we fix this? And how can we make this run a lot faster? And why is it running so slow? Well, the reason it's running so slow is because we are constantly recalculating answers. And every time we have to do addition, that uses up our processor and makes it take a lot longer to calculate the answer. So for example, if we're calculating the Fibonacci of 38, that means we're going to calculate the Fibonacci of 37 here, which is then going to ask us for the 36th, and then we're going to go over here and we're going to do the 36th again, and same thing with all the other numbers below that. Now that is extremely inefficient, and that is why we're going to learn how to write a recursion statement, which is a lot more efficient and takes constant time rather than exponential time, meaning that every single term we add is going to take an extra, say, 0.1 seconds rather than exponentially increasing per term. So let's start off. This is new, so we have to make something called a a hash table or a dictionary in Python. So in Python it's called a dictionary. So let's just say nums is equal to, and then our little squiggly brackets like that. Curly braces, whatever you want to call them. Now we're going to make a new function. In this case I'm going to call it fib1. Same thing, same parameters here with n. And then we're going to start off the exact same with our base case. So we're going to take if n is less than or equal to 2. If n is less than or equal to 2, we are going to return a value of 1. Now here is where things change just a little bit. So like I mentioned before, we don't want to recalculate an answer if we've already calculated it. So what we need to do here is we need to check if we've already calculated that answer. So if n in nums, meaning is that inside of our table or inside of our dictionary, then we're simply going to return the value that's in there, which is a lot faster than recalculating that value. So then we're going to return nums of n like that. And now here, this means we have not already calculated the value, so we do have to go ahead and do the recursion to calculate that. So otherwise, we need to, in this case, we're going to set a number. We're going to set a variable. We're going to say num is equal to, and then the same thing that we typed here. So this is our recursive call, Fibonacci of n minus 1 plus n minus 2. We're going to add this to our table. So nums n is equal to num, and then we are going to return num, just like that. Now I went a little fast, so we'll just recap it really quickly. What we do is we first check for our base case. If we have that base case, we return 1. Otherwise, we see, have we already calculated that value? So if we already calculated the 7th term, yes, we have, okay, so let's return it. Now let's say we have not calculated that value. We go down here, we do the same thing we did up here, and we do our recursive call to calculate that value. We store that value under the key n, and then we return that value. So now let's try running this. So again, sorry, I just need to change this to fib1 so we're not referencing this function up here, which would defeat the whole purpose of doing this. And now I need to print out fib1 of, let's do a 100. Let's see how long that takes. And there you go. Almost instantly, we have that printed to our screen. Whereas if I tried to do fib100 running this function up here, well, this would be an hour-long video. So let's go and go to 200 now, see if we can handle that. There we go. Obviously, we have tons of digits, and let's keep going up to maybe 300. Yep, 300 works as well. Now, I want to show you when we get capped off. So I'm going to try 1,000, and there we go. So we actually do run into an error here. Now, this is more specifically with Python, but in other programming languages too, you can see this error here. So maximum recursion depth exceeded in comparison. So when you try to compare too much and the calculation gets extremely large because of the Fibonacci sequence, that's the way it works, it actually stops us from doing that. But otherwise, you can see why this is a lot faster than this by simply adding an extra 3 or 4 lines of code. Now, all that being said, I hope you learned what recursion is and how to use that. If you want me to do another example or another problem, leave a comment below. We can do some more advanced recursion with something with more than one base case, just like this. So yeah, if you liked the video, please like and subscribe, and I will see you again in another.